Hello, and welcome back to the course. Today we're going to look at the Cauchy-Goursat theorem, which in the end might not be as impressive. It's basically Cauchy for triangles. We'll prove Cauchy for much more complicated path than triangles. But the idea behind this will be to prove that the assumptions that we're coming into the theorem with. Okay, so this is subsection 3.2.2 in the book. All right, so let's start. So a set is convex. You know this already. If the segment between any 2 points in X is in X, right? So if you take any 2 points in the set, draw a straight line between them, that entire line is back in the set. That's what we mean by convex. Now, let 3 points A, B, C be non-collinear, so they don't all lie on a single line. Now we define a triangle. We're going to call it T. Was these 3 points as vertices as the convex hull of these 3 points. That means the smallest convex set containing the points, or the intersection of all convex sets that contain the 3 points. In other words, there's another way of writing this. If you write it as this combination of A, B, C, where the T1, T2, and T3 are just something in between 0 and 1, and they sum to 1. So all these points are going to be, well, that's going to be T, right? It's the set of those points, right? But it is the convex hull. It's the smallest convex set containing the points, and it is the triangle that you normally think of. All right, so if we have, A, B, C, that's the triangle, right? And we orient the triangle in such a way that we're thinking of going around the boundary of the triangle counterclockwise, right? So that's the orientation on the boundary. And so one way to write it is to write it as a chain, right? Starting from A going to B, right? That's A, B, and going from B to C, that's B, C, and then going from C to A, so C to A, right? So that's giving you the boundary as a cycle, right? Now, a key thing here, and it's a key thing that comes up. It's this triangle. Whenever we're talking about triangles in this course, we mean the solid triangle. So we mean the entire thing, not just the boundary. So the boundary is one thing, but the T is everything inside, right? So all the points inside. It's the convex hull, right? It's not just the 3 lines making up the triangle, right? It is the solid triangle. All right. So here is the theorem, right? Here is Cauchy-Goursat. So suppose that we have some open U. We have a holomorphic function on this open set U, and we have a T inside U, a triangle. Then what we get is that the integral around this, the boundary of this triangle of f with respect to dz is 0, right? So that's the theorem. Now here it is important that the entirety, not just the boundary of T, but the entirety is inside U. We're not supposed to go around any hole, right? So you cannot, have a hole in U and then draw, just the outside of the triangle around that. That's not a triangle that we're considering. We want the entire solid triangle inside U. And the name Goursat is really because of what we're assuming right now. So we're assuming that f is holomorphic. So that means that f is complex differentiable at every point. But what we haven't proved is that means that f prime is continuous, right? Now, if you have that f prime is continuous, all this stuff becomes much easier, and that's really what Cauchy was assuming. So the big idea here is that all we're assuming here is that f is complex differential at every point, right? We're not assuming anything about the derivative, right? We're not assuming the derivative is continuous. All right. I mean, we're going to prove at some point that the derivative is actually holomorphic. But right now we don't know that yet, right? That's the point. That's why it's Cauchy-Goursat, not just Cauchy. All right. So how do we prove this? We prove the contrapositive. Now, for contrapositive, we're assuming that f is continuous. So we're just going to do this for continuous functions. And basically, we're going to start with a continuous f, and we're going to suppose that there is some triangle T, like this, where the integral is not zero, right? And what we're going to show is that that means that there exists a point in U, it's actually going to be a point in this triangle T, where f is not complex differentiable, right? That's the that's the strategy, right? So we're assuming that we're going to call this the absolute value of this integral. We really only need to worry about the size of this integral. We're going to call that c. So c is some positive number, right? Non-zero positive number. And we'll find a point where f is not complex differentiable, right? So we start with a t, and we cut the t into 4 subtriangles by basically dividing each side in half, right? And so then we have these 4 subtriangles that make up our big triangle, right? Our big triangle T. All right, now, if we orient each of these TJs positively, counterclockwise, then something that you will notice is that these, we've added some edges, right? We've added these internal edges. And what you notice about them is that the orientation of the whenever the 2 triangles meet, right, the 2 smaller subtriangles meet, the edge is oriented exactly the opposite, right? So for T1, we're going like this, right? And for T2, we're going like T4, sorry, we're going like this, right? So we're going in the opposite direction on these inside edges. On the outside edges, well, I mean, there's nothing that's going to cancel, and it's we're actually going in the right direction, right? It's the same direction as the outside, the big triangle, right? Okay. So with that, we notice that we can rewrite the integral around the boundary of the large triangle as the sum of the integrals around the small triangles, right? I mean, that's an integral around a longer thing. I mean, we're sort of going around these things twice, but that's fine, right? That those will just cancel, right? So we get that this big path integral is the sum of these 4 smaller ones, right? All right. Now, if this path integral is c, just because, I mean, some number, right? Some non-zero number. If we add up 4 smaller numbers and they add up in absolute value to c, right? One of those numbers, at least one of them, maybe more, at least one of those numbers is at least a quarter of c, right? c over 4, right? Or bigger, right? I mean, in absolute value, right? So, all right. So let's label whichever that triangle is. It's, maybe T2 or something, right? So we're gonna, we're gonna label that T super 1, right? So now we need sort of to decorate our triangles in two different ways. So we'll let T super 1 be, if it was T2, it'll be T2, right? There's a, first level of, reduction. We're going to keep doing this, right? So now we have a triangle, T1, T super 1, where the integral around the boundary of this triangle is at least C over 4. And this T1 is half the size of our original one, right? All right. And we keep doing the same thing. We start with T1, and then, we cut it up exactly like this into 4 subtriangles, right? And we notice that the integral over one of the boundary of these smaller subtriangles has to be at least a quarter of C over 4, meaning C over 4 squared. So we'll label that guy T2, right? You don't worry that there's maybe like more than one of these, just at least one, right? Pick the one that does it, right? And there may be another one, but who cares, right? Just pick one that does it. All right, now rinse and repeat, right? So you keep doing this ad infinitum, right? You have a sequence of triangles, TK, right? Such that when you integrate around their boundary, over here, you get C over 4 to the K. All right, now all these triangles are nested, right? They all, they're subsets of each other. We keep cutting the triangle in half, right? These are similar triangles. We're cutting all sides to a half. That means that the diameter, the largest distance between 2 points in the set, right? That's what the diameter is always a half of the previous one, right? So if we take a look at tk minus 1 and take 1/2 of that, that's the diameter. It's exactly the diameter of tk, right? And the diameter of if we take the diameter of t divided by 2 to the k, we get precisely the diameter of tk, right? Now, another way to think about the diameter, it's basically the length of the longest side, right? That's the diameter of a triangle. All right. Now, all these triangles, and note we are talking about solid triangles. These triangles are compact sets, right? We have a nested intersection of compact sets. One of the things about compact sets is that if you do have that, if you have a nested intersection of compact sets, and you take you have a nested sequence, of compact sets, and you take the intersection, you get a non-empty set for the intersection. So the intersection is non-empty, right? Now the diameter also goes to 0, right? So in each iteration, the diameter halved, right? So we cannot have more than 2 points in the intersection because they would be some positive distance away from each other, and so they can't eventually be in one of these triangles, right? And it's in an intersection. They're supposed to be in all of these triangles, right? So that means that the intersection is non-empty and it can't be more than 1 point. It is exactly 1 point, right? It's exactly 1 point. We're going to call it Z0, right? That's the point. That's the intersection of all these triangles. All right. Now, let's write f, our function that we're interested in, as the value of the function at Z0, right? This fixed point, Z0. Plus, some linear term, right? Plus some continuous function g, right? F is continuous, right? So g is continuous, right? Alpha is just some constant at this point, right? So we can always, write it for any alpha, right? We just write this, g is some function, right? That's just defined by that equation. Now, if f was complex differentiable at z0, then there would be some alpha, namely the derivative, such that if I take g and I divide by z minus z0, that this would go to 0, right? Because that's the error when basically computing the derivative. That's how you would compute the, if it was differentiable, that's how you would compute the derivative, right? That's the difference. That's the thing that's supposed to go to 0 to make the difference quotient work out, right? All right. So g over z divided by z minus z naught, that should go to 0 as z goes to z naught, right? For some alpha, for the alpha that's the derivative, right? And we're showing that there is no such alpha, right? So we'll prove that this thing never goes to 0, no matter what alpha you pick, right? So alpha is just some random alpha, and we're just going to show that this never goes to 0. Now, so let's fix some specific alpha. Now, if g at z0 is 0, we're done. Yeah, it's clearly not going to 0, right? Because for this to go to 0, I mean the denominator goes to 0, so the numerator had better go to 0 as well. G is some continuous function, right? So if it's not 0 there, yeah, we're done. It's not going to 0, right? So let's assume that for this particular alpha, g at z0 is 0, right? That still doesn't say that this guy goes to 0, right? It's still something that we'd have to check. Now, Cauchy's theorem for polynomials says that since this guy is just a polynomial in z, right? Z0 is some fixed number, right? And you don't need all of the, the Cauchy's theorem for polynomials. You could compute this very directly, but basically the integral around any triangle of this guy is 0, right? So that means that the integral around this triangle for f is the same as the integral of g, right? So we can just go to g, right? So we know something about the integral of f around the kth triangle, right? Namely, it's bigger than or equal to c over 4 to the k. All right, well, that's the same as the integral of g. And we bound that as above, we bound this above by the the arc length integral, right? So this is just going around the triangle and trying to just integrate with respect to the arc length as we're going around, right? So that's the triangle inequality for integrals. Now let L be the length of the original triangle, the big one, T. The length of the kth triangle, right? Because all the sides are always cut in half. So the length of the boundary of this triangle is L over 2k. And it's important that this is 2k and this is 4k, as we'll see momentarily. All right, by the mean value theorem for integrals, right? There is some zk on the boundary of the kth triangle such that the if you evaluate the absolute value of g on that, which now we're thinking of just some continuous function, it's equal to the average of g over this. Now here it's important that we're doing this integral with respect to the arc length guy. So if you can write this as one big integral of a continuous function, right? Because g is continuous, right? If it didn't have those absolute value bars on the dz, right, the derivative would flip. That would be a discontinuity. But here there is no discontinuity. It really is, it can be one big integral, Riemann integral of a continuous function, right? So there is some point z on this triangle, on the boundary of this triangle, where this integral is exactly that. All right, now because this g is 0 at z0, zk cannot be z0, right? Because this thing is not 0, right? I mean, it's bounded below by there's also this guy you have to divide by, but anyway, it's not 0, right? This is not 0, right? So therefore, zk is not equal to z0, right? Now, if just to make things simpler, let me call d the diameter of the original triangle. So because zk is on the kth triangle, and d is the diameter, and so d over 2 to the k is the diameter of the kth triangle, we get that the distance from zk to z0 is at most d over 2k. All right? So let's now show that this thing cannot go to 0. So basically, we've produced a sequence of points that go to, right? This means that zk go to z0, right? Which is clear because they're in these nested triangles whose intersection is just z0, right? Right. So let's see what this sequence of numbers does, right? I claim it doesn't go to 0, right? So that means that g of z over z minus z0 cannot possibly go to 0 if you have a sequence of guys that doesn't go to 0. All right. So we've bounded from below. So we first start with this bound, right? We have a bound above for the denominator. So we get a bound from below for this thing, right? Now, this guy, well, we know that that's equal to this integral, right? That's basically the way that we defined what zk was, right? So we add that in, right? And we get an L over here, and now we get a 4k over here. And now we use this bound, right? That we know that it's c over 4k, right? And the 4k now, because it was this 2k and this 2k, right? And this 4k, and that everything just canceled out nicely, right? So we just get c over dl. Namely, this guy does not depend on k, right? It's some non-zero number, whatever it is, but it does not depend on k, right? So this thing cannot possibly go to 0, right? As k goes to infinity, right? Therefore, because we have that zk goes to z0, this thing cannot possibly go to 0 as z goes to z0, right? Meaning f is not complex differentiable at z0, right? Which is what we wanted to prove. Now, a useful version of this that sometimes comes up is, and this sort of argument comes up quite a bit, that you just have a continuous function on a triangle, right? Now, T is a closed set, right? So it doesn't really make sense of talking about a holomorphic function. But T has an interior, right? The interior of this closed set is something, the interior of the triangle. And let's suppose that this continuous function is such that if you restrict it to the interior, it is holomorphic. Then you're supposed to prove that the integral around the boundary is 0. And basically, you'll have to do, in some way, you have to pass some limit under the integral, right? Because what you have in the theorem is that if f was holomorphic on something larger than t, then you could have done this, right? But now you have it's actually holomorphic on something smaller than t, but just barely, right? So you're going to have to do some sort of limit, right? Either make fit smaller triangles to the inside, or maybe rescale that. There's a bunch of different ways of doing this. Okay, so that's an exercise. All right, so so next time, what we're going to look at is we're going to look at the Cauchy theorem for a much wider class of well, and in some sense, we did it for a wide class of sets, open sets, but very few paths, right? So the thing that we're going to do next is for a very wide class of sets, not all open sets, just star-like open sets, but for all paths, for arbitrary paths in certain open sets, we're going to prove Cauchy, and so. Right. So that's what we're going to do next time. And Goursat is actually important there, right? That we have Cauchy for triangles. All right. So see you next time.